Hi everyone. Today we are really happy to have Brandt Gaches, who's a postdoc at Chalmers University in Sweden. Brandt, you have about 1 hour in total to present your work and get some questions.
Mhm.
The floor is yours.
Yeah, first off, thank you very much for inviting me to come and give this talk. Hopefully it's quite interesting and get some good discussions going on afterwards, maybe for things to do in the future. So yeah, today I'll be talking about the kind of first paper in a series presenting these simulations called the High Resolution Accretion Disks of Embedded Protostars, or HADES, as the acronym just so luckily happened to end up. And today in particular, we'll be talking about how the magnetic field of the protostar impacts the mode of accretion from the protostar. So as Raphael said, I'm a cosmic origins postdoc fellow at Chalmers. Um, Although in a couple of months, I'll actually be starting an MBA Nuclear fellowship to start my own research group at the University of Duisburg-Essen. I also want to thank my collaborators who, without this work, this probably wouldn't have been possible. So Jonathan Tan, Rolf Kuiper, and Anna Rosen. So first off, I just want to motivate why we do these system missions in the first part, why we care. And there's still a big fundamental question within the field of star formation for how do protostars actually accrete their mass. So I've shown here kind of one of the more kind of typical pictures that I'm sure maybe everyone here has seen of magnetospheric accretion. This is the kind of fiducial model for how protostars grow their mass, where you have some truncated disk where it's truncated by the magnetic fields, and gas basically flows up to this truncation point and then flows along magnetic flux tubes from the disk surface to the protostar surface. And this is kind of canonically the picture for more, especially more evolved protostars like T Tauri, where we have a lot better observational constraints, and I think where most of the simulations and the theory has been focused on so far, in part again because we have a lot of observations to actually constrain this. But very young protostars, which are still heavily embedded in their cores, one still have the cores sitting on top of it. The disks are generally much larger, so a few to 10% of the mass of the star is still in the disk, and their magnetic fields of the protostars may be weak, may be strong. We don't really quite know. There's kind of constraints all over the place. But unfortunately, if you go out looking for the magnetic field of a protostar, there's a bit of degeneracy versus if it's weak versus unmagnetized, because eventually you don't get your signal anymore. And so you end up not being able to really constrain below a certain limit. So we kind of wanted to ask the question of, does magnetospheric accretion still occur in these phases? Or really what is the actual mode of accretion as kind of a function of the protostar's magnetic field? One of the other kind of key questions is to try and understand the variability of the accretion. So I've shown here, this is for T Tauri. So these are low mass protostars that are not embedded anymore, so they're quite exposed. And this is this nice a diagram here, where you see kind of this multi-filamentary accretion happening onto a protostar. It kind of all dumps on at some point, and then you get basically an outburst. And you see, this kind of light curve on the bottom for this type of object. You see as variability on the order of a few days, and it's just kind of periodically kind of going up and down. And we really want to understand that we do see that some earlier protostars are variable as well. So we want to understand, kind of where this variability might be coming from, how much of it is powered by the accretion versus other processes that might be occurring. So when trying to understand these type of problems, of course, the first thing you do is you go and you do a paper search to make sure no one has done what you've done before, or if they have, what could maybe be expanded upon. So we really went and did a bit of a deep dive, and it turns out there's really kind of two phases that have had a lot of very good high resolution numerical simulations. And by high resolution, I mean actually resolving the accretion physics or some sort of, the relevant physics that you're interested in. I've shown here, this is completely non-inclusive of all the ones that are out there. This is just the kind of ones that I picked out, in particular ones that have very good visualizations. So for students out there, if you want your slides, if you want figures like this, make sure you have really good visualizations because it makes it easy to put in talks. And you see that this is the kind of core collapse. So you start with some protostellar core that's quite large, and you let it collapse down to its first or second hydrostatic phases. At this point, you can kind of say this is maybe a class 0 protostar, or Larsen core, or somewhere around these regimes. And here you can get to very high resolutions through nested grids or SPH or things like this. And there's been a lot of exploration into what physics is important from here. So I've shown here these are all non-ideal simulations here, both 3D for the VTET and Verster system simulations, and 2D for Asmita Bandari's simulations. And these have shown a lot as to what physics are really needed, or what physics are regulating these kind of first core collapses. At the very opposite phase of this, or very opposite end of this, we have a lot of numerical system simulations. Again, I've just pulled a few here out as well, that have studied the kind of T-Tori phase. And what I mean by this is because most of these are done with dimension-free simulations. But what I mean is kind of low protostellar disk or low disk masses compared to the central object, low accretion rate. So accretion rates around 10 to the minus 19 solar masses per year, and generally much thinner disks as well. And again, there's kind of been a mix here of both 3D and 2D. And very often now, I think, though, these are being pushed to 3D quite a bit, which is excellent. But what you can see is that there's this massive gap in simulations for protostars. We have a lot of stuff at the very early phase, a lot of stuff at the very end phase, but most of the mass is accreted in this kind of between phase, when you still have a kind of well-defined protostar with a disk around it. But the disk is then quite massive, and it's accreting at rates of 10 to the minus 7 or 10 to the minus 5 solar masses per year, or even higher if you go to higher mass stars. And this phase has really been missing a lot of high resolution simulations. And I'll note that a lot of this is probably not because there's been kind of neglect, but because there haven't been a lot of good observations right up until recently that could help you constrain these things. But recently, there's been a number of surveys from Eleonora of Fiorino, where they've gone out and done some pretty good estimations of the accretion rates and disk masses and protostellar masses for a large range of objects, particularly in this kind of class 0, class 1 phase, this kind of early embedded phase. And I've shown here from two of the different papers phase. The one on the left shows the accretion rate as a function of the disk mass, and the one on the right shows the disk mass as a function of the stellar mass. So of course you could always try and flip these things to all the same one. And in particular, I want to highlight that the kind of red and purple dots in these on the left, and the kind of red and yellow points are kind of showing the kind of class 1 style protostars. And the kind of red or the black box is kind of where the simulations are kind of meant to be. So we wanted to simulate something that's like 1 solar mass protostar, and this thing kind of constrains what your disk mass should be. So in this case, the disk mass for these simulations is about 17.5% of the mass of the sun. And this kind of puts it within this box. It's a bit above the line in this kind of blue hatch region you see here. This is where you would expect on large scales there to be gravitational instability. We don't resolve this because we don't do the large scales. And in our case, we have a kind of a marginally magnetized disk. So the plasma beta in the midplane at 1 AU is set to be 10 to the 5. So what are the simulations that I'll be talking about? So these are the HADES simulations. We use fairly ad hoc initial conditions, and this is because we're doing very high resolution, so we can only simulate for on order kind of days at a time, or kind of months at a time. So it'd be much harder to kind of find the initial condition initially that kind of works. Although in the future we'll try and do this. But we kind of start with some reasonably kind of ad hoc initial conditions, and then run these more so as kind of numerical experiments than trying to simulate a specific type of or a specific object. So we start with a power law surface density profile and the disk, and a power law density profile for a core. Although I note that the core largely gets thrown out anyways by the outflow ejection. The temperature we use in initially just power law as well, although future simulations hopefully will actually have a bit better initial kind of way of setting the temperature, so everything is in nice hydrostatic equilibrium. And then for the magnetic fields, we have both an hourglass magnetic field. This is initialized with a vector potential and kind of shown here as these streamlines here in the picture on the right, which is showing the initial distribution. But then we also include a static protostellar dipole field. And this is meant to be the kind of generated field from the protostar. We include non-ideal physics. We have the ohmic diffusion and Hall effect. We have a kind of an alpha viscosity, which is really there just to set a floor on the viscosity. And then we have we only include gravity basically through a background potential for the protostar. In this case, our disk is not really massive enough to become where the self-gravity becomes important. We have line cooling, and then some X-ray heating, which helps the the kind of very inner region stay a bit stable. And we use 2.5D in spherical coordinates. And then we use the logarithmic grids in Pluto. This is very nice because we can get very high resolution on the inner parts. And then, of course, a bit less resolution on the outer parts. The maximal resolution we have is about 10 to the minus 4 AU near the protostar. And this results in about 10 to the minus 3 AU out at about 1 AU, which is the end of our domain. So this is showing here the full domain from the surface of the protostar out to 1 AU. One of the problems with getting these things set up and stable is because the disk is very massive, you end up with fairly high Alfvén speeds and just gas flows as well. And because we have very high resolutions, our time steps end up sometimes tanking down to the order of like 10 to 100 milliseconds. And so if you want to evolve for months at a time or something that's reasonable, you need a huge amount of time steps. And so this ends up, these simulations we each run on a cluster with about 500 processors each. And we were simulating it almost in real time for a while, where a month on the cluster was about a month of evolution time. So because most of the plots you'll see, we only go about 60 days of evolution with outputs every 30 minutes. And most of this we weren't able to evolve it much longer just because we couldn't have it be on the cluster indefinitely. So kind of very initially, before we talk about the accretion, just wanted to just show the very large scale morphology. So we run 4 different simulations from this paper, going from 10 Gauss up to 2000 Gauss of the protostar field. And these plots show both the large scale, and you see the kind of 3 zoom-ins that are going into the very inner region, where the kind of first box is about 0.1 AU, and the very inner box is about 0.02 AU. And you can see that kind of going between the different ones, you see fairly significant large-scale differences, particularly in the outflows, where you have a fairly kind of collimated kind of outflow thing that's going on for the 10 Gauss, versus when you go to 2000 Gauss, not only do you see a one-sided outflow, but you see kind of a more open wind on that kind of top hemisphere. You can kind of also initially see from the zoom-ins a bit spoilers for how the accretion is going to happen, because you see for the 10 Gauss, the disk is fully impacting the protostar, versus at 1000 or 2000 Gauss, you actually start to see a properly truncated disk. So I'll just jump in to kind of look at how the magnetic field varies. So you'll kind of see on the left here, this is showing the accretion rate versus time, and the color lines are just the raw accretion rate for the whole protostar surface at every output. So we have 30-minute cadence, so you see it's squiggling quite a bit. And then the black lines you see there are just rolling averages, where it's a day-long rolling window, so it kind of smooths out a lot of that very rapid variability, so you can get kind of a more idea of what the systematic variability is. And then we'll kind of go through the order of the different magnetic fields. So for the 10 Gauss, you'll see here, again, we see the accretion rate, the red line showing where you are in the movie. And then down below is the density field. You see a lot of the accretion is happening not only along this kind of mid-plane streamer, but 2 kind of flows along the disk surface. These are largely the results of not only kind of failed winds that then cycle back down, but also just gas sliding along the disk surface into the protostar kind of medium or kind of high latitudes. This type of accretion, for instance, was also seen by Shinsuke Takasawa in his 2020 paper, around that, where he did a kind of an unmagnetized protostar. And you end up with kind of 3 filaments that are kind of dominating. This mid-plane filament. I don't know how much it should be trusted in that because it's 2D, you have current sheets that then can't really properly reconnect there. And so maybe this is something where, you know, in 3D you would see it either go away or change. But you see, you know, kind of in terms of the overall accretion, it's, you know, relatively stable. And then you see a lot of very fast, rapid variability as you have a lot of turbulence in this in accretion region that's just throwing gas down onto the surface in a highly turbulent environment. You see from the video every once in a while you have an outflowing gas, kind of an outflow from the surface can knock one of those filaments away and drop the accretion a bit, and then it kind of stabilizes and goes on. We can then look at 500 Gauss, and you see here the kind of systematic variability has dropped down a bit, but so has also the amount of this rapid variability has also decreased quite a bit from the 1,000 or from the 10 Gauss. And if we look at the video in this kind of very inner 0.1 AU region, we can kind of see why. And that's the 500 Gauss magnetic field is not enough to truncate the disk, but you can induce a bipolar outflow. And this bipolar outflow is dominated by the magnetic field, and the magnetic pressure is able to kind of squish the accretion disk down away from the high latitude regions and focus it into the midplane of the protostar. And so you get this kind of what we kind of call in the paper a kind of outflow enhanced boundary layer accretion, where the presence of this bipolar outflow that's kind of dominated by the magnetic field is able to kind of contain and focus the accretion flow in towards the protostar. And you also see that this, because the dipole component now becomes, you know, reasonably useful in the midplane, this kind of midplane streamer is now gone. So this midplane streamer only really shows up in the unmagnetized cases because you don't really have any other component besides these kind of hourglass fields. We can then go up quite a bit more to a 1,000 Gauss field, and now you see there's a bit more systematic variability as it's going up and down, up and down. But the kind of rapid variability again has decreased even more. So this rapid variability seems to decrease as you go to higher and higher magnetic fields, as your accretion region is kind of becoming a bit more ordered and less dominated by just turbulent flows smattering onto the surface. So we can kind of then see what happens for 1,000 Gauss, and here we get a very strong one-sided inflow. This has been seen in some other two-dimensional simulations of magnetospheric accretion. So in 3D, this picture might change at least a little bit. But you see that there's generally still at least one or two of these columns going from a kind of marginally truncated disk onto the surface at high latitudes, and there's a lot of gas flow kind of flowing along these two regions. The disk in this case is only marginally truncated, as you can see, and there's sometimes where the disk actually fully kind of falls in and you see a little burst of accretion. But then at 2,000 Gauss, something changes quite a bit. So you still, now you get a very clearly truncated disk. You get a kind of a fairly stable truncation point. And as you just saw there, I can maybe, let's see if I can back it up a little bit here. You see that at this, there's like a little dot of gas here that kind of falls in every once in a while. And so what we end up seeing is that even though there's kind of a marginal low level amount of accretion from a magnetospheric-like mode of accretion, there's these huge bursts of accretion that are where a lot of the mass is actually growing, that are being dominated by gas kind of building up at the truncation point and then being fed into the protostar via instabilities. We did some kind of investigation, and most likely it's like an interchange like instability. Because when you actually like put magnetic field lines onto this thing and everything, you see that you get a pretty stable point, and every once in a while a streamline is able to kind of connect itself to the protostar surface and dump matter onto it, and then it restabilizes and kind of goes like this. So this seems to be kind of what the picture is when you go to these very high magnetic field cases, is you have some degree of magnetospheric accretion, but then a lot of mass is being dumped onto the protostar in kind of bursts that you see in this kind of very systematic burstiness via instabilities from the truncation point. And we can kind of look a bit more at why we might think this might be kind of at least related or somewhat like an interchange like instability. So here I'm going to introduce the fastness, the fastness, parameter. For those who aren't familiar with it, it's the ratio, basically the rotation of the star, over the rotation rate of the disk at the truncation point. And of course, because what you're really wanting to care about is actually the relationship between the corotation radius and the truncation radius. But the disk at the corotation radius is rotating at the same speed as the star, so you can just use the omega star here. And so what we kind of see is that for the 1,000 Gauss case, this factor kind of sits at around 1 with an occasional dropping below it. And I've shown on the left, so the top left is for 1,000 Gauss, the bottom left is for 2,000 Gauss. There's kind of two regions. The first is kind of below 1, and the other one is below 0.6. And below 0.6 is kind of where simulations that are in 3D in particular have seen that you can induce the interchange instability at the truncation point. And again, those are generally tailored from 3D. This is 2D, so there's going to be some differences there. So this isn't meant to be taken as like this value means this, but kind of given that we see systematic differences within the fastness parameter, that this is telling us something about the mode of accretion. So what you see for 2,000 Gauss is that whenever you see one of these big bursts of accretion, such as kind of just before 30 days, you see kind of around it increases in the accretion as well. So these things appear to be a bit correlated, where you can kind of see here around this accretion burst is when matter all of a sudden dumps onto the protostar, bursts in accretion, and then things kind of restabilize at this point. So it seems like we're kind of looking at an instability-driven mode of accretion, and we can kind of investigate this by saying, so I forgot to mention it, the initial the protostar in our simulations is assumed to be rotating at a third of the Keplerian breakup speed. So if we slow it down, what happens then? So if we slow the protostar down, we can then slow it down to say 10% of the breakup speed, and now you can kind of start to see that a lot of that very large variability has gone down. So this is also for a 2,000 Gauss protostar. So it's the same initial conditions. All I've done is just slowed the protostar down, and you get a lot more kind of steady accretion. You get kind of something that looks more typical like a magnetospheric accretion. And we can go one step further and say what happens if we slow it down even more. So 5% breakup speed. So really slow this protostar down. You end up with something that looks even better. It's very stable accretion at this point. You see a bit more systematic or kind of rapid scale variability. But you see something that, if you were to just take, an individual picture of this like this, you would say, oh, this is magnetospheric accretion or something like it. Great. We know how to solve this. We know the physics of this. So it's not really then just the magnetic field that, of course, matters, but the spin rate of your protostar. Unfortunately, for early embedded protostars, these are two of the most unknown factors for protostars and for star formation. So we did a little bit of investigation for this because we want to give some guidance as to what this could be. So yeah, unfortunately, really understanding the mode of accretion that actually occurs in star formation relies on understanding or kind of constraining two of the kind of more unconstrained parameters that we have in star formation. But hopefully, maybe this motivates people to be able to really go out and try and constrain this. So we can kind of put it all together to put together a kind of story of protostar accretion. So if you have your protostellar magnetic field is less than some critical field, whatever this critical field may be, to truncate the disk. If it's much, much less than this, you end up with something that's like a turbulent boundary-layer accretion. So gas is falling from the disk directly onto the protostar. There's a lot of turbulence. There's a lot of rapid variability. If it ends up getting kind of close to this critical magnetic field, so strong enough that you can start to get kind of an outflow that's being generated by the presence of this dipole, but not enough to truncate the field, you end up with this kind of outflow enhanced boundary layer accretion. And this would be this kind of outflow enhanced boundary layer accretion is kind of more typical of the kind of pictures and diagrams you see from like the old clay model of boundary layer accretion, where you have a thin disk that's kind of hitting into the equator of the protostar. If you're able to truncate the disk, so your magnetic field is stronger than this value, then it kind of again splits off again. If your kind of fastness parameter is much, much greater than 1, you end up with this kind of classical magnetospheric accretion. Conversely, if it's the flipped, so if you end up with a fastness parameter that's much, much less than 1, you end up with a kind of magnetic instability-driven mode of accretion. So then you'll end up with a very kind of systematic variability that goes up and down, and not a lot of stable accretion over time. We can kind of then see this story visually by looking at these kind of plots here. This is showing where the accretion momentum flux, so just rho VR is, as a function of the latitude on the surface of the star and as a function of time. And this, I think, visually tells this story quite nice. So for 10 Gauss, you see it's basically raining down on the field all over the place. You see, kind of presence of filaments that are kind of continuous for times, and then they disappear for a short time and then reappear and disappear and so on. But once you go to 500 Gauss, it's very much so constrained to the kind of plus or minus 20, 25 degrees from the equator. It's still a bit turbulent, but it's much more constrained. When you increase this magnetic field, you end up with two kind of well-defined filaments that are kind of hitting the protostar at kind of higher latitudes of 50 or so degrees above the equator. And they're relatively stable with you see the kind of occasional dips down to the surface. And finally, at 2000 Gauss, you see there's kind of two weaker filaments, but then you see these big nodes of high momentum flux that are hitting the midplane of the protostar. And this is actually where a lot of the mass is happening. So you see this kind of relatively stable-ish kind of magnetospheric accretion in the kind of background with these instabilities driving kind of pulses of mass to the equator. This is nice. This is great. But one of the things that really people care about for starvation models is also not just what mode of accretion, but what's the filling fraction of that accretion. And this turns out to be kind of a complicated question to answer. And part of this is because there's also a lot of low-level amounts of accretion, meaning it's a kind of accretion where the total accretion rate is kind of negligible to what the total accretion rate is for that time, but it's still there. If you just say how many cells along the surface have net accretion versus outflow or zero. So, VR greater than 0 and density greater than 0. It turns out that it's like, generally quite high, 75, 89%, but most of that is by low level of accretion that doesn't actually play really any significant role into what the accretion rate is at that time. So then one could say, okay, well, what if we just kind of weight do a kind of an accretion weighted average along this. So we only pick out really the cells that are there. Well, part of the problem is if you have very high resolution, you end up with very well-defined streamers, and you end up with accretion rates that are like 0.1% or something, which is much smaller than even magnetospherical models would do. And that's because you're mostly dominated by one small tiny filament that attaches there that has very high accretion, but because it has very low area, it actually doesn't do as much for the overall amount of accretion. So instead, we kind of derive this kind of other way, where we sorted basically all of the cells on the surface of the protostar by their momentum flux, so rho VR. This tells us where the most amount of kind of momentum is being transferred into the star, or really in general then where the kind of momentum per area is being, or the accretion rate per area is being delivered. And then we basically marched down those cells, as you kind of see here on this diagram on the left. We kind of marched across this and added up the amount of mass and the amount of area that's being covered there. And then we can say kind of from this kind of plot, for the top 10% of where the mass is, what's the covering fraction? For the top 50% or 50 or 90% of the mass that's been gained, what's the total surface area? And you get a plot that looks a bit like the one on the right. So when we talked about the accumulated mass fraction, this is the kind of top massive fraction. So where the kind of most of the accretion is happening and then down. And you see then it kind of goes up so that at 100%, you get close to 100% of the area. This is for the 10 Gauss field. So we would kind of expect this because it's all hitting the surface. But you see it kind of goes up very fast. So we can then kind of plot, though, for the contours for this for 10%, 25, 50, 70, 75, and so on percent. what this is. I think this plot is actually for the 1,000 Gauss here. Or no, the 2,000 Gauss field, because you see the accretion rate going all over the place. And the table on the right shows what the kind of filling fraction of accretion is using this model. And one thing that's a bit remarkable is that if you look at where the top 90%, so where the vast majority of the accretion is happening, it's relatively insensitive to the end protostar magnetic field. And you see it kind of goes up as it gets to this 500 Gauss, okay, where we did talk about how it's outflow enhanced, so it focuses it, so this is maybe a bit more understandable. But, it kind of sits around 10%, which is what a lot of people who are doing kind of subgrid modeling for star formation have been assuming anyways, is around 10%. So that's both kind of, I guess, a good thing, that our results kind of agree with what people have done in the past. It's a bit of a bad thing because unfortunately it means it's nothing super new, but we did at least numerically confirm that these values are reasonable guesses. So finally, in the paper, we really looked at what variable would want to observe. So I've shown here now, I've converted from kind of accretion rate to accretion luminosity. And you see that, again, for the kind of 10 Gauss, it's very, very rapid versus at 2,000 Gauss, it's much less rapid. And so one might ask the kind of reasonable question, what would an observer actually see kind of in a more systematic or statistical way? So the way that we did this is we looked at the YSOVAR kind of cadence, because they had one of, I think, the best cadences, some of the best estimations of the variability, in part because they did this really clever thing where they had a kind of a logarithmic sampling curve where they went very rapid and then spaced it out and then repeated this pattern over and over again. And this allowed you kind of over 30 days to constrain not only kind of longer term variability, but also shorter term variability. So within this kind of blue band that you see on the left, we basically did a synthetic YSO light curve by basically, choosing a random point within this blue band and then sampling it at basically this kind of rate. But this gives you, say, 1,000 different light curves that'll all be quite variable. And then you want to ask, what would the kind of average trend be? So you take 1,000 samples and you average them. And that's what's shown here on the left. This is for all the different magnetic fields. The black lines are the individual YSOVAR cadences that were chosen within this kind of blue band. So you see now the time axis only goes up to about 26 days, which is the length of this kind of synthetic cadence. You see that the black lines still show a good amount of variability along each individual line. But then if you want to ask what would the average trend of this be, you would average these up and you get what's kind of shown on the right. And unfortunately, what this means is that a lot of this variability is washed out if you kind of looked at the average trend. However, the degree of the variability here agrees fairly well, actually. It's about 0.3 magnitudes with what YSOVAR has seen so far for class ones. And in the paper, we actually call out a few protostars, I can't remember them off the top of my head, from the YSOVAR sample, where the light curves seemingly are kind of somewhat similar to what we find here. And in particular, I want to point out that for the YSOVAR, sometimes there's a few protostars that you see it kind of go up and then kind of start to slide down a bit. And they assign a period to this, which is fairly similar to their observed period. So either you have a period that roughly matches their observed period, which, maybe not, or you have a declining profile that you're truncating at some point and you're kind of inducing then because if you look for variability in your phase fold, that maybe, you will oftentimes find period signals that are the same length, right, as your observed period. But this seems to be roughly consistent. But really what this kind of tells us that we need to really look at kind of more protostars in a more systematic way, especially more rapidly and for longer times. Hopefully then this paper can help motivate observers to be able to ask for this amount of time, because it is kind of a bit of a ridiculous ask for these types of things. But if they can have at least a good plot that says, okay, this is what we're trying to look for, then maybe that will hopefully be able to get them more time to actually look at the protostar variability. So since then we've looked at a bit beyond the accretion, so I want to kind of finish up very briefly with talking about some of the ongoing projects with these system simulations. So one is I have a student who's now starting a PhD in physics, but she started this as part of the CASM summer program, which, by the way, if you have students who are undergrad or master's program, the CASM program here at Chalmers is open right now. So we have a lot of there's a lot of really great undergrad and master's level kind of research projects for the summer, and they get to come here for to Chalmers for 2-ish months and do some research here. So this is one of the projects that was started in 2023, looking at the outflows instead. So I've shown here, this is the ratio of the outflow over the accretion for the different magnetic field lines shown in the colors, and a different radii kind of cut through the disk. And really what I want to call attention to is the bottom line. This is the cumulative ratios for this. So there's a lot less variability, but basically you're adding up the total amount of mass that's been in the outflow and in the and gained by the protostar and dividing them. And at 1 AU, which is in this kind of far left on far right on the bottom, we get values that are kind of roughly consistent with 10 to 30%, which is oftentimes the value that people have put in for their subgrid star formation simulations, that, you know, kind of 10 or 25% or whatever of the gas that's gained by the sink particle gets ejected by the outflow. So we seem to be relatively consistent with that, which is good news. So maybe we're getting something at least close to right. We also then looked at the kind of individual wave launching or outflow launching from the protostar. So this is again in the different columns showing the different magnetic field cases. And then what we've done is for different angular cuts. So this is now theta from the top. So 20 degrees is kind of in high latitudes, 75 is approaching the disk. Along each kind of angular cut, we plotted as a function of radius and time where the mass flux is. And so, for instance, for the 1,000 Gauss case at 20 degrees, you see these really nice kind of what look like streamers, right? And these are actually waves that are propagating kind of along a kind of theta axis. You can, of course, get a slope from this and get a wave speed. But one thing that is kind of interesting to look at is as you go from the high latitude to the disk midplane, you go from seeing kind of individual waves that are launching out to a kind of a more systematic bulk outflow. So we seem to kind of be seeing both the kind of accretion powered outflows at kind of the kind of higher latitudes and the kind of bulk disk outflow in towards the disk, which is kind of what one would expect anyways. Finally, there's been 2 master's projects that are been kind of looking at this. So one, we took the HADES simulation, just downscaled the mass of the disk by like a factor of 100 to get something like a T-Tauri star. This was a master's thesis here at Chalmers from Thomas Tour. I've shown here on the left, this is just a snapshot of the density and temperature field. You see a nice truncated disk, but he ran a few of these models and looked at the where the truncation radius is as a function of this kind of b squared over m dot. And if you look at, let's say, the Hartman relationship, this gives this exponent of 2/7, and he gets something that's a bit shallower. So maybe there's something going on here with the non-ideal physics and everything that's changing this. So we're hoping to maybe look at this a bit more. If anyone's interested in this, we'd be happy to work with other people on this as well. And finally, there's a master's thesis ongoing where we've instead scaled everything up to basically an 8 solar mass protostar, and are looking then at kind of 2 cases right here out to much further radius. So we've kind of scaled everything up so that it's kind of all self-consistent. So the left is a 50 Gauss field, and the right is 2,000 Gauss for a high mass protostar, so 8 solar mass star. Kind of not playing them at the same time. And you see that there are still quite a bit big differences here. You see at 2,000 Gauss when you see actually accretion powered kind of magnetic powered outflows that are really driving a big cavity here very fast, versus the kind of 50 Gauss, you see kind of it's more like a kind of conical wind maybe. We haven't really looked into this much detail. And for 2,000 Gauss, maybe if you squint in this kind of zoom in panel, you see we are starting to marginally truncate the disk. Not much, but marginally. So because it's so massive, it is a bit puffier, so this helps. We can start to see some truncated ones. The master student, who is also looking for a PhD, by the way, is now running also a 4,000 Gauss model to see if we see it actually continue to truncate. So to conclude, these new simulations are really enabling a very high resolution investigation into the accretion and outflow physics from early embedded protostars. However, they really require kind of a multi-physics prescription to stay stable. So we really need non-ideal MHD. We have a variable ionization fraction that's in there. This has been needed because assuming a constant one, the disk is very massive and very dense, and so you end up if you versus the outflow, which is not. And so depending on you can't really then choose a good constant ionization fraction that would be good for the whole domain. So we have a variable ionization fraction. But this allows the simulation to be stable. So from the initial conditions, we can run it without Pluto crashing or anything for a long time. But because we have very high resolution, where we have very fast waves, right now we've been constrained for using the HLL solver in Pluto, so it's a bit more diffusive, but we have very high resolution, so maybe this is still kind of okay. We're hoping that if we include some better physics in the future with radiation, maybe things will be a bit more stable, so we can go to some better, more accurate solvers. But we'll see. There's also in Pluto, there's a limitation on what solvers you can use with the Hall effect right now. I think hopefully in future ones this will be changed. One thing we do find is that the accretion morphology changes quite systematically, but kind of what I would say smoothly as the magnetic field increases. So we can kind of create a cohesive story. We only, though, see for the very highest magnetic field cases, large-scale systematic variability that occurs over kind of weeks or days. So if you go out hunting for protostar variability and you don't see this kind of very large-scale variability over weeks or days, either there's reprocessing of the emission in the disk, washing out your signal, or it could be that these kind of protostars aren't actually highly magnetized. So far, the simulations seem to agree decently with kind of observations and previous theory. Now we can really start to really delve into the physics, right, and probe why these things are happening, why we get these values. Future simulations, which are currently planned, will include a bit more physics. So working with Rolf to include radiation pressure and ionizing radiation for the high mass stars, and an active stellar surface. I actually had this initially, but without self-gravity, the surface just constantly falls in and it's useless. So hopefully now with better physics, we can include an active stellar surface to maybe get proper shocks on the surface of the protostar and things like this. So these are all things that we have interest in the future. So if any of you are also interested in these things, feel free to reach out. We're happy to expand the collaboration, or the HADES submission is really thought to be more of the idea is to have kind of a framework of looking at embedded protostars at very high resolution. So we're always happy to have more people join in the effort. Thank you very much. So any questions, critiques, concerns, conundrums, all fine with me.